Imagine you're on a crowded dance floor. You and your partner are moving perfectly in sync, gliding through the crowd without a care. But suddenly, the beat drops, a chaotic mosh pit forms, and a surge of people violently bumps into you, tearing you and your partner apart. Stumbling, you frantically reach out, trying to grab onto anyone just to keep from falling over. This exact sequence of violent separation and frantic searching is happening right now, at a microscopic level, inside the core of every operating nuclear reactor. Inside a running reactor, cooling water is locked in a violently chaotic chemical dance. If you look at a nuclear power plant from the outside, you see a massive, perfectly still silhouette. Deep inside the internal reactor coolant system, the naked eye sees a pool of still, hot water, bathed in an eerie blue glow. That blue light marks where intense nuclear radiation is constantly bombarding the water molecules surrounding the core. The radiation carries so much raw energy that it does more than just heat the water. It physically hits the molecules so hard that it shatters the liquid itself. A water molecule is stable, one oxygen holding two hydrogen atoms. In radiolytic decomposition, reactor radiation blasts the molecule, instantly snapping its chemical bonds and sending the pieces flying. These broken pieces become free radicals, highly energized, incredibly unstable fragments. Just like a dancer trying to keep from falling, free radicals are desperate for stability. They will blindly latch on to the very first thing they bump into. Because the radiation is constantly creating millions of these fragments, the water is transformed into a highly reactive chemical soup. If the reactor is constantly shattering its own water, you might expect the whole system to eventually run dry. However, the entire reactor is a tightly sealed, highly pressurized closed loop. Those broken, frantic pieces have absolutely nowhere to escape to. Because they're trapped together in this confined space, the unstable fragments inevitably crash right back into each other. When they do, they pair up again, reforming into stable water molecules through a process called recombination. This creates a cycle called dynamic equilibrium. Every second, billions of water molecules are shattered, while at the exact same moment, billions of others are stitching themselves back together. Inside the core, the water exists in a permanent loop of shattering and healing. But there is a hidden danger caught inside this cycle, the loose oxygen fragments. If an unstable oxygen atom happens to bump into the pristine metal of the reactor walls or fuel rods before it finds a hydrogen partner, it will grab directly onto the metal. This creates corrosion, or rust, which weakens the metal and produces debris that can clog up the system. Left unchecked, the oxygen born from the shattered water would slowly eat away at the heavy metal core from the inside out. Engineers prevent this by manipulating the odds on the atomic dance floor. Operators deliberately pump a massive excess of harmless hydrogen gas directly into the coolant system. By flooding the water with extra hydrogen, they guarantee that whenever a molecule breaks apart, the oxygen fragment instantly bumps into a hydrogen atom and reforms back into water before it can touch the metal walls. This hydrogen inventory actively suppresses oxygen and neutralizes the threat of rust. A nuclear reactor is a meticulously engineered environment where human ingenuity harnesses the chaos of radiation, forcing shattered water to continuously rebuild itself.